Good morning, everyone. We'll do a quick sound check. Please report in the questions tab if you are able to or are not able to hear us properly. Great. So it looks like the audio is fine. Again, a very warm welcome. Thanks for joining us today. My name is Saurabh Kumar, and I'm on the marketing team here at H2O.ai. I'd love to start off today by introducing our speaker. Meg is a customer data scientist at H2O.ai. Prior to working here, she worked as a data scientist, building products driven by machine learning for B2B customers. She has experience working with customers across multiple industries, identifying common problems, and designing in Mountain View, California, and holds a degree in applied mathematics. Before I hand it over to Megan, I'd like to share a quick few webinar logistics. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. This webinar is being recorded. A copy of the webinar and slides will be available after the presentation is over. Without further ado, I'd now like to hand it over to Megan.
Hi, everybody. This is Megan Kurka, and thanks for the introduction. I'm a data scientist at H2O, and today I'm going to be talking about getting your feet wet with machine learning. So this talk is going to cover an introduction to machine learning and also the products that we offer in H2O. And I'm going to be giving a couple of demos, one with H2O3, which is our core machine learning platform, and one with our new product, Driverless AI. Okay, so just a little bit about the company. We were founded in 2011, and our products include H2O open source in-memory prediction engine, driverless AI, sparkling water, H2O for GPU, and enterprise Steam. And I'll be discussing those in more detail today. Our mission is really to operationalize data science. So how can we get you to move very quickly from building a machine learning product and putting it into production? Here's the list of our product suite, just to highlight the different products that we offer. Our first is H2O. It's an in-memory distributed machine learning platform. It's written in distributed Java. We also have Sparkling Water, which integrates that same H2O AI platform with Spark. Makes it very easy to use H2O in your existing Spark pipelines. A new product we have is H2O for GPU. This is lightning fast machine learning on GPU. It uses a CUDA C++ backend to optimize GPUs for machine learning. And then the last product I'm going to mention today is Driverless AI. Driverless AI is our automated machine learning platform, which is optimized by GPUs as well. The last product is Steam, and Steam helps support secure multi-tenant H2O clusters for our H2O and sparkling water products. Okay. So first, I kind of wanted to cover just a little bit about what machine learning is, so everyone can understand how these products can be used in a practical sense. So what is machine learning? Machine learning is really about finding patterns in your data to predict something that's of value to you. So in this example, we have some yellow dots, some blue squares. How can we separate these two groups? How can we learn patterns in the data that will separate these two types? Now in a more, let's say, real life use case, rather than separating circles and squares, we may want to predict how much a customer will spend or whether or not a customer will churn. These are just two examples of how to use machine learning. But really, if you have a column in your data set or a feature that's interesting for you to predict, you can apply machine learning to that to help you make smart decisions. Some of the machine learning algorithms that we offer in our H2O core platform are linear models, random forest, gradient boosting machines. We also offer deep learning, a feed-forward, fully connected neural network, and stacked ensembles, which will actually combine multiple algorithms together using a superlearner. Unsupervised learning algorithms are also offered on our platform. We have clustering. So this would be maybe finding groups of similar customers, maybe finding groups of similar products, There's many different uses of clustering. We also offer feature extraction, so how to kind of represent your data in a way that's more optimal for a machine learning model. So for example, we offer word2vec, which will take text and convert them to numbers, which is much easier for artificial intelligence and machine learning to understand. The last unsupervised learning algorithms we offer are anomaly detection. So can we detect any strange records in our data? Can we detect maybe fraudulent customers, maybe some anomalies in our data? So that would be our autoencoders, generalized low rank model, and principal component analysis that we offer. So all of these are different types of use cases for machine learning. They're all offered in our H2O platform, which I'm going to discuss in a little bit. But before that, I just want to discuss the typical machine learning pipeline. So this is what a data scientist will typically do when they want to build a model. They may have data from multiple sources that they'll integrate together. There probably will be some data cleaning steps, maybe adding new columns. You'll finally get this table for modeling. So these are the features or the predictors I want to use to predict a certain target. So maybe I want to predict whether or not a customer will churn. I can use these features to predict that. I'll build a model, and this is an iterative process. Maybe you'll try different algorithms, different parameters. Maybe you'll add new columns to your data that could help. And then you'll finally end up with your final model that can be used to productionize. Okay. So let's talk a little bit about how H2O can help you with this typical machine learning pipeline. What is H2O? So I did mention that it's this open source in-memory machine learning engine. One thing I want to discuss is that every algorithm is written in distributed Java. So all of our algorithms, the GBM, deep learning, etc., they're all written in distributed Java. What that means for you is that they can scale. So you can actually train models on very large data. The data does not have to fit on one machine. It can fit on multiple machines, and you can train a machine learning model on that. We also offer different APIs to make it very easy for users to adopt. We have R and Python APIs. And what this allows is the user to connect to a large H2O cluster, possibly running on Hadoop or Spark, do their machine learning from R and Python, but being able to leverage this large H2O cluster. We also offer a web UI called Flow, which I will be demoing today. That allows you to go through a machine learning workflow without writing any code. It's point and click. Here's a typical H2O cluster. H2O itself is just a jar file, so it can run locally on Hadoop, on Spark, which I'll talk about with sparkling water. On the cloud, it's very flexible. In this case, I'm showing a picture of H2O running on top of Hadoop cluster with multiple nodes. H2O is distributed in memory, so we can have the data across multiple machines, as you can see here, different pieces of the data. And we can use this H2O cluster for very fast model building. So just a little bit about how the H2O cluster works with the different APIs. We may have a cluster running on my computer, on Hadoop or Spark. How does it work from an end user perspective? Let's start an H2O cluster up. And I'll be a data scientist on my local computer using R. So here's RStudio. The same will work for Python as well. What I may want to do is do some data cleaning, maybe add new columns, maybe build a model. I can do that all by writing R script, and this will all connect to my H2O cluster. So this H2O cluster in this case could be multiple machines, multiple JVMs. The data will be distributed across that cluster, and it will be using a REST API to send commands to that H2O cluster. Nothing is actually going to happen on R or Python. This is really great when you have very large data that won't fit into your local computer. I do want to talk a little bit about sparkling water. Sparkling water, again, is that same H2O platform, but on top of Spark. Why use sparkling water? Well, it allows you to leverage your Spark cluster. The machine learning, H2O machine learning engine will be on top of your Spark cluster. It also helps allow you to use Spark data munging. So you can actually leverage the Spark functionality in the H2O cluster. We offer functions that allow you to seamlessly toggle between a Spark data frame and an H2O frame. What this allows you to do is use Spark for its data munging capabilities, and then you can convert that Spark data frame to H2O to train an H2O model on it. Sparkling water also allows you to leverage Spark pipelines. You can incorporate these H2O3 models into existing Spark pipelines, which allows you to excel in adding these advanced machine learning algorithms to your Spark workflow. Now here's our sparkling water cluster. It looks very similar to the cluster before. We have some Spark cluster running on Hadoop in this case. And all that happens with sparkling water is we start H2O on top of that Spark cluster, and Spark and H2O are connected, allowing for that seamless toggle between the two types of data frames. At this point, I want to switch over to a demo. Today, we're going to be demoing H2O3 on Hadoop. The data is our Freddie Mac single-family loan level data set, and our goal is to predict whether or not the mortgage loan will terminate unfavorably. So here's a little snippet of our data set. We have different features about the loan applicant, like their credit score, their debt-to-income ratio, and we also have information about the property. So where's the property located, how many units, where's the zip code of the property, and then we have information about the loan. So we know the first payment date of the loan, the maturity date, we have the interest rate, different features like that. And finally, we have delinquent, which is a true-false column. Does the loan become delinquent or not? Okay, so we're going to go and dive into this demo. I'm going to just exit out of my PowerPoint and switch to my Chrome. All right, so first things first, I'm going to check and see what my cluster looks like. I'm going to go to admin, cluster status, and I can see that I have a H2O cluster on Hadoop with 3 nodes, each with about 10 gigabytes of memory. Firstly, I'm going to import my data. We're actually going to be importing data from HDFS, so I'm going to start by writing HDFS, and my path will autofill. We have my Freddie Mac data, and I'm going to click on my data that I'm interested in importing and import the data. The first step I'm going to have is to parse the files, and it's going to ask me to set up the parsing schema. It already automatically detected that it was a CSV parser. We can take a look at the columns in the first few records of the data. Data types have been automatically assigned. Our column, our target column delinquent, has been assigned numeric because it's 0 and 1s. We're going to switch this to enum or categorical so that it really treats it as a true-false column. And we're going to parse this data. The data is being ingested into H2O across these 3 nodes, and we're actually going to get a data summary. This took less than 5 seconds. Our data is about 16 million records with 29 columns. Here we can see the data summary. So not only did it ingest 16 million records of data in less than 5 seconds, but it also created this automatic data summary for me that gives me information about each of my columns. Here we have credit score. Credit score is an integer. We have min, max, and mean values. We can actually click on a particular column to get more information about that. So I'm going to click on credit score and learn more about this column. Here I see the distribution of credit score. So typically people have credit score within 700 to 800 range, but we can get an idea of the shape of the data in this way. Let's try to build our model. That's our real goal, to see whether or not we can predict if a loan becomes delinquent. I'm going to start by splitting my data. I can click this split button. What this is going to do is it's going to split my data into 75% train, 25% test. The reason for that is I want to predict how well the model performs on some holdout data set. So I am going to manually remove 25% of the data so we can evaluate it. And we're going to split the frame. Once this is done, I'm going to select, go to my model menu, and here I can select which kind of algorithm. This particular demo, we're going to try a gradient boosting machine, but you can see all those algorithms we had mentioned earlier: distributed random forest, deep learning, we have XGBoost, and principal component analysis, all of those unsupervised learning algorithms as well. So I'm going to click on gradient boosting machine. And now it's just going to ask me to kind of fill in this form to build a model. I'm going to select my training frame, which is what we've decided train would be. I'm going to select my validation frame, which is test. So this is what I'm going to validate the model on, see how well it performs. And then it's going to ask me for my response column. So what am I trying to predict in this particular problem? Here I can see all the columns, but I want to predict delinquent. We can ignore any columns that we know are not helpful to the model. I'm going to ignore the loan sequence number, which is the loan ID, positive termination, and zero balance code. These both have information about how the loan ended. I don't want to use them because it'll be data leakage. It will affect the model, make it much more accurate than it actually will be. Okay, so let's start by building this model. I'm going to leave all of these parameters as default, but you can see there are quite a few parameters that allow an expert data scientist to optimize or kind of customize their particular model. Okay, we're going to click Build Model. The model has started running. Interestingly, with H2O, we can actually watch the model as it builds, so I can refresh this and see as it builds. I'm going to go to my admin and check out the CPU meter. And here we can see the 3 nodes in my cluster working. So the work is distributed across the 3 nodes. Let's go back to my flow screen so we can see how it's doing. So far it's built 20 out of the 50 trees. We can see that as the number of trees increase, the scoring history, the log loss decreases. So our error is getting better as we add more trees to our data set. Below that, we can see the training metrics, the AUC, the ROC curve on the training data, and that same curve on the validation data. And the model finished building. It took about, let's see, 42 seconds to train 50 trees, each with a depth of 5 on 16 million records of data. We can see the ROC curve for the validation data. We can actually play around with it and get confusion matrix. Below that, we have variable importance. So how does the variables, how important are each variable in predicting delinquency? So credit score is very important, also the state of the property, and when the loan will become mature. We have gains and lifts tables. The last thing I want to point out is the POJO. So this is a plain old Java object. This is actually exportable Java code that represents the model. This is what makes it very easy to move this model into production. So all of the logic found from this GBM model is in the Java code. If we look a little bit down and take a look at the Java code, we can actually see that this is just a series of if-else statements. So this is GBM is an ensemble of decision trees, and each one is being coded into an if-else statement in Java. So this is very easy to productionize. I'm going to toggle over to another flow I have open with a smaller set of data. For demo purposes, I want to show one of our new capabilities in H2O called AutoML. So I'm going to click on Run AutoML. This is different from the GBM we just built. It's actually going to require very little information from me, just the data I want to train on, a response column, so our delinquents. We can ignore any columns we don't want to use, so we're going to ignore those same columns. We can select to exclude any algorithms. What AutoML is going to do is it's going to actually run all of the algorithms if I don't exclude any, and it's going to do parameter tuning for me as well. So this makes it pretty easy to get a head start on which algorithms are the best, what parameters are optimal, and so on. And we can watch as this builds. So the AutoML automatically split my data into training and validation. We can monitor this live. It's building a random forest model. It will build 2 random forest models, GBM models, GLM models, and deep learning models. And finally, it will do a stacked ensemble on this. So our first model is almost finished building, our random forest model. And it will come up in our leaderboard, which will be sorted by AUC. The best is first. So we finished building our first random forest model with an AUC of about 0.833. We can let this run and we'll get a complete leaderboard with our best models on top. Each model has a Java object that we can export for production. Okay. That ends our demo of the H2O3 product, which is again in distributed Java. I'm going to switch over now to talk about some of our new products which are optimized for GPUs. Okay. First, we're going to talk about H2O for GPU. This is our open source GPU optimized machine learning platform. H2O for GPU is written in C++ CUDA. It has a Python API, and it does have a public GitHub if anyone's interested. The algorithms we've so far implemented in H2O for GPU are GLM, SVD, XGBoost, and K-means. Above that, you can see the speed up, the comparison of how it performs using CPUs versus GPUs. So there is a large speed up, especially on K-means. XGBoost most notably, I would mention, because that's one of our algorithms that are heavily used in our driverless AI product. And driverless AI does use this H2O for GPU platform underneath the hood to allow it to leverage the power of GPUs. So let's talk a little bit about driverless AI, which is our newest product. Okay, driverless AI does does automate the last 3 steps of the model building or machine learning workflow. It'll automatically create this modeling table for me. So it'll make new features if that helps. It'll do model building, and it will give me the final optimal model. So this last 3 sections of the machine learning workflow are automated. Driverless AI incorporates speed, accuracy, and interpretability. Speed by being able to use that H2O for GPU in the backend. Accuracy, we do automated feature engineering, which I'll discuss in more detail, which helps improve accuracy of our models. And interpretability, so it allows you to interpret your model, understand how this model is making the decisions that it does. Accuracy, so we do have automatic feature engineering, and we do ensembling, tuning, and optimization of our models. Here is our performance in different Kaggle competitions using no human intervention, just having driverless AI run the model. So we ended up top 1% in the BNP Paribas competition and top 5% in the Amazon Kaggle competition without any human intervention. Now this will take weeks for somebody to do manually. Driverless AI is able to do this very quickly. It's able to automate the feature engineering and model building process, so it's able to try many different combinations very quickly. Here's a look at the platform. It's automatic feature selection, feature engineering, and model building. I'm going to go through this in more detail during our live demo, where we try to, again, predict whether or not a loan will become delinquent. So what's feature engineering? I just want to give a little bit of background about that so everyone is familiar. Feature engineering is trying to change the way your data is represented to help improve the performance of a model, of a machine learning model. So let's take a very simple use case. I want to predict whether or not someone will take the day off. The only information I have is the date. So how can I build a model to predict this? Well, if I only use date as my only feature or my only predictor, I'll have very low accuracy. But I can change the way the data is represented. So I can add, expand this date column into maybe month, day, day of year, the year, and the day of week. So I can get a much more accurate model just by representing the date in a different way. So this is one example of feature engineering. Driverless AI does that date expansion, but it also does much more. It will do automatic cross-validation, target encoding, frequency encoding. It'll do something called truncated SVD to reduce the dimensionality of my data. It may segment my data using clusters and use those segments to help improve the model. It also automatically handles text data, which helps improve the performance if you have any text data, maybe customer feedback, for example. So driverless AI will incorporate some of these original features. In this case, we have some interest rate, debt to income, number of borrowers, but it'll also automatically create these new features like the target encoding of the state. We also have some target encoding of clusters and so on. Oops. All right, so I'm going to go and start our demo of driverless AI and walk us through that. All right. So let me make this a little bigger. So we're going to start our experiments by, okay, here we go. We're going to start our experiments by importing some new data. I'm going to go to our data sets and add a data set. And just for a little bit of background, I'm running this on Amazon AWS with GPUs. So I'm going to click on Add Data Set. Now I can either click it from import it from a file system, Amazon S3. We also have an HDFS connector if you have HDFS. So I'm going to import it from my file system in this case. I have my data saved in Data, Freddie Mac, and we're going to import the training data. And we're also going to import some testing data. The test data is going to let us know how well the model performs. I can start by actually, let's say, visualizing our data. So I'm going to click on Visualize. And this will give me automatic graphs of how the data set looks. So I can take a look and start exploring my data. It's different from other platforms, I would say, with visualizations because it's going to be automatic. I don't need to graph things manually and choose the columns I want to look at. It's automatically going to tell me the interesting things in my data set to focus on. So for example, I can click on correlated scatter plots and see different columns in my data set that are correlated. So the loan to value is correlated with the CLTV, which is another representation of loan to value. Okay. We can also click on outliers and see a list of the outliers in our particular data set. So here we have an outlier with a very high interest rate on their property. If we click on the outlier, we can see those particular records. So these are people with maybe lower than normal credit score. Okay, we can take a look at them. So this gives you an idea of how your data set looks. If we go back to my data set tab, we're going to, again, try to predict whether or not a customer or a loan will become delinquent. So I'm going to click on Predict. And all I have to do really is give it a target column. So what am I trying to predict for? Again, in this case, we're going to try to predict if some loan will become delinquent. We can give it our test data set to see how well it performs on a test data set. And we can drop any columns that we know are not helpful or maybe have some leakage information. So I'm going to drop, again, positive termination, the zero balance code, and our loan sequence number, which is just the loan ID. The rest of the parameters I'm going to leave as default. We do have experiment settings that control how accurate the model is, or different methods, let's say, to improve accuracy. So accuracy will increase the number of models used for parameter tuning, number of folds used in cross-validation, and the number of models used in the final ensemble. Time represents how many iterations driverless AI does, and interpretability represents how interpretable the final model is. So let's start by building this. First thing it's going to do is tune the model backend. It did drop some columns with all missing values and also with constant values. Okay, so it began by parameter tuning. Sorry, one second. It begins by parameter tuning the model. It's going to do 2 out of the 34 models for parameter tuning. We can click on our GPU usage and we see that all of the GPUs in this particular machine are being utilized. Once it's done parameter tuning, it's going to do more feature engineering. Now, the interpretability controls how interpretable the model is. This means also, too, how interpretable the new features are that are automatically created. If we take a look at our feature engineering, we actually see that a lot of the top features are not in our original data. So our first one is the mean of the response of our cluster IDs. So it did some clustering and calculated the mean delinquency rate. We also have different features. We also have different features like some interaction terms, cross-validation target encoding, and some of the original variables. And it's going to keep updating, so you'll notice that this keeps changing as the best model changes. Hopefully our AUC will keep increasing as it finds the right representation of models. We can examine how well the best model is doing with our ROC curve. This will give us the confusion matrix in different points. So how many times do we get the delinquency correct and how many times do we get it wrong? We also have lift and gains in the UI that'll tell me how well the model is performing compared to some random guess. It keeps building, and we've just changed the best model. Actually, almost all of the top variables are not in the original feature set. A lot of them are automatically created. We've already run this for 2 minutes and already have about 336 new features. And we've already scored about 130 of the 570 models that will be done in this particular experiment. So you can imagine how much faster this makes a typical machine learning workflow. We've already tried a lot of combinations of new features and many different settings of model building. So I'm going to let this continue running, but we're going to take a look at an experiment that already completed with the same data set. So here's my completed experiments. We can see how the AUC improved over time by changing the representation of the features. And we're also given a summary of the data. So 253 features were tested in this particular version, and only 53 were selected. So we are doing feature engineering and feature selection as well. We can see the final ROC curve. And now we can actually interpret the model on the original features. So I'm going to go into that in more detail. Before I do, I want to point out that we have a scoring pipeline that you can download. This is independent of driverless AI. It holds the logic of the feature engineering and the model scoring. So it'll allow you to kind of export this, take a regular raw record. It'll do the feature engineering, give me the final model score. This uses Python runtime. So let's go and interpret this model on the original features. Here we can see the way the model is making the decisions based on the original data. The reason why we show this on the original data is because some of the automatically created features may be hard to understand. So maybe the target encoding of the clusters that we had seen previously, maybe truncated SVD, maybe the text transformations, those can be difficult to interpret. So we do the interpretability on the original features. We do also allow you to do the interpretability on the transformed features if you're interested in that as well. So here we can see the top features in our original data in predicting whether or not a particular loan will become delinquent. So the most important feature is the state, the seller. We also have credit score coming up, maturity date, and the original interest rate. Now, variable importance only shows me how important the particular variable it is. It doesn't show me what the relationship is between that variable and the prediction. And the reason for this is that the underlying algorithms used are nonlinear. So the relationship may not be linear. It's not easy to just say positive or negative relationship. However, we can use the partial dependency plots below. And this will show me the relationship between the feature and the probability of delinquency. So here we can see different credit scores, and the yellow is showing me the average probability of whether or not a loan will become delinquent. So it looks like the rate is relatively high. It's almost at 10% until the credit score gets above 600. And then it keeps decreasing, and we see a plateau again at a high 700 level. So this gives me an idea of how the model is making its decisions. Its credit score is highly related, and the higher the credit score, the less likely the loan will become delinquent. Okay, we can also select different columns to explore. So maybe we'll take a look at the maturity date. Maturity date also has a relationship with the prediction of delinquency. It jumps up. If we take a look at the first payment date, we can see it jumps up at about 2006 to 2008. So if the mortgage started in 2006 to 2008, we have a higher likelihood of delinquency, slightly higher. On the left side, oops, let me go back. All right, on the left side, we can see the decision tree. So this is just a small decision tree. It only has level of depth 3, but it does give you an idea of how the model segments the data into loans with high risk of becoming delinquent and loans with low risk of becoming delinquent. So we can see a particular leaf node here with about a 31% likelihood of becoming delinquent, so pretty high. And these are people with a credit score lower than 690 in particular property states, and so on. So we can get an idea of where our high risk segments in the data are. All right, above that, we can see the model interpretability. Global model interpretability plot. Now what this is showing me is actually individual loans. Each white dot represents an individual loan. And these loans are ranked or ordered based on their model probability of becoming delinquent. So our loans that have the highest probability of becoming delinquent are on the upper right-hand corner. The loans with the lowest are down below. If we hover over a particular loan, we can see some information about them. So for example, we can see the model prediction, whether or not it actually became delinquent, and also reason codes. So why did this particular loan become delinquent? So we're going to click on a particular person. Let's click here. So once we click on this person or this loan, we get more gray information now in the whole model interpretability plot. This is showing me, for example, the gray line is showing me where they fall in the decision tree. So they do end up in this really high probability of becoming delinquent segment. Okay. I'm going to click on a particular customer and go to explanations. And now we can get an understanding of why this particular person is likely to become delinquent. So the reason why is related to their, first payment date. So their first payment date was in 2007. The loan term, but also the interest rate. The interest rate is a little bit higher than typical in the data set, so it increased the probability by about 30%. Okay. Here's another reason code we can take a look at. So this is another first payment date, 2006, which increases the likelihood. Their interest rate increases it, but they have a pretty good credit score, so that decreases the likelihood. So we get an understanding of exactly what makes up this person's probability of becoming, or this loan of probability of becoming delinquent. Okay, so let's close this and go back to our main screen. We can also see in the above information the scoring pipeline. So this is another external scoring pipeline, but this also incorporates the reason codes that we just examined. So not only can we use driverless AI to automatically get these probabilities that a loan will become delinquent, but we can also use it to get the reason codes about why a particular loan has a high likelihood or low likelihood. Now, driverless AI is not limited to this example of trying to predict whether or not a loan will become delinquent. It also supports regression use cases. So maybe we want to predict how many inches of rainfall. It also does multinomial classification. So maybe predicting a type of class. So I'm going to go ahead and close this MLI, and we're just going to go back and take a look at our feature, or at the experiment that we had started earlier. So the experiment did complete, and we can take a look at the top features. They're actually all clustering features. So this particular experiment clustered the data by the credit score, the maturity date, and the loan term into 5 clusters, and the most important feature is the target encoding of that cluster. We also have the target encoding of state. We did see that state was very important in our H2O3 models. State is also important here, but it's not represented as state anymore. It's actually the target encoding of state. One of the major benefits of driverless AI is that it can optimally handle categorical columns so that it's not, let's say, harmed by high cardinality categorical columns. But we still do see some of our original features. So we do see the original interest rate, original UPB, and the loan to value. In this particular use case or particular experiment, one second, we have 447 features tested, 56 were selected. We did 35 models trained for parameter tuning, 142 models trained for feature engineering, and 26 models trained for the final ensemble model that is used as a final model. Now, this only took us about maybe 5 minutes to run, but it was able to try many, many different combinations of experiments or model building, which would take a lot longer for someone to manually do. Okay. So we'll take a look at downloading the scoring pipeline. This, as I mentioned, is the external pipeline that will do all of these feature engineering, like the cluster target encoding, the interaction terms, and the categorical target encoding. Each scoring pipeline is specific to the experiment that was run. We can also download this experiment summary to use for later on. And we can download the test prediction. So we did tried this on the test data set, and we had an AUC of about 0.87, which is higher than if we ran it with just H2O3 without any feature engineering. Feature engineering does really make a large difference in the accuracy of the performance. So I think that that concludes our demo. I'm gonna go to my slides. And thank you, everybody. So I want to hand it over to SK to start talking about some of the questions.
Thanks, Megan. We have some great questions in the chat window. We'll try to get all of them with time permitting. The first question asks, I have a model built in H2O, say a GLM model. Now I want to import that model in Python to use for other apps. How can I do that?
All right, great question. So if you have a model built in H2O, one of the great things about that is that they always come with exportable code. So you will have that Mojo, that Java code that can be used for deployment, used for different applications. We do have customers using our Pojos and also Mojos, which are different type of the Java export in different pipelines such as Spark, Hive UDF, AWS Lambda. So it really is very flexible. It's very easy to turn this Java export into a WAR file if you have any web-based applications. So it's really, I would say, almost limitless in how you can productionize this.
Great. The second one asks that they are interested to know the claim of H2O's algorithms if they are better than other implementations.
Great question. So H2O3 is an open source machine learning platform. One of the benefits of H2O3 is that it does make it very easy to train a model. We do automatically handle categorical columns. For example, we automatically handle missing values. Some other open source platforms may require one-hot encoding, for example, ahead of time. Additionally, H2O is distributed. So if you're using maybe scikit-learn or R, you can get all these great algorithms, but it may be hard to train your model on the full data set. You may have to sample down. So H2O3 allows you to do that on the full data set. Driverless AI, on the other hand, is, I would say, very different in the fact that it does the automated feature engineering, which does have a huge impact on the accuracy, how to represent these features in the most optimal way. So this makes it, I would say, different from, let's say, other open source products because it's able to do this automatic best representation of your data and try endless experiments on it.
Great. Third question asks, what are the capabilities of Flow when it comes to data processing and, data pre-processing and EDA?
So Flow allows you to do EDI, exploratory data analytics. It will automatically, let's switch over to Flow. It'll automatically allow you to see the representations of your data. So we can take a look at my data. We'll take a look at the trained data. We can see a summary of all of the statistics, but we can also click on different features and get information about them. So we may want to look at, for example, the delinquency column, which is what we were trying to predict. We can see that most of them are negative, but we do have some delinquent loans. So we already get an idea of how balanced our particular data set is. It makes it very easy to do exploratory data analytics. For pre-processing, we do allow for merging different data sets in Flow. However, I would say that you get a lot more feature engineering and pre-processing capabilities in our R and Python APIs. The reason being is that you can actually write code in R and Python. So you really have a lot of ways to customize your data set. You can replace NAs, you can filter your data, you can add new columns, and so on. And this can help improve your model performance. One of the unique things about H2O3 and Driverless AI, however, is that it automatically handles NAs. So you do not need to do any, let's say, NA pre-processing. Those are all handled by the algorithms.
Thank you, Megan. The next question asks us, can the trained parameters be obtained other than the Pojo or Mojo form?
So can the parameters used to train be obtained other than the Pojo and Mojo form? Yes. So if we take a look at our model, list all models, we can see our GBM model that we created. Our GBM model has, we can download the Pojo or the Mojo. So that can be used, but we can actually export the model in a binary form, which is can be ingested by H2O. Now this will have all of the model parameters as well as all of the validation statistics you're seeing here. Not only that, but I would say that you can also save the code you use to train your model, and that will have the parameters as well. I would always recommend saving the code and saving the model. The model is not that big, and that way you can always reproduce it.
Great. How is H2O support for elasticity to add more nodes to cluster if required and ramp down after modeling is done?
So for elasticity with H2O3, we don't have, let's say, dynamic or elastic clusters. The size of the cluster is decided at the beginning when you launch your H2O cluster, and it remains that size until you shut it down. If you do realize that you actually need more compute power, it's recommended to shut down and start a new cluster. It's very easy. The reason why we don't just allow you to add new nodes or new machines to the cluster on the fly is because one of the important things about H2O is how the data set is distributed. And the reason why is because H2O does focus on machine learning. Now, if the data set is not distributed evenly, it will not improve the time of adding new nodes will not improve the time of building a model. The reason for this is that all the nodes will have to wait for the node with a large amount of data on it, and it doesn't speed anything up. So we do recommend starting the cluster up, H2O cluster up, seeing if that's enough size for your data. Our rule of thumb is about 4 to 5 times the size of the data for the H2O cluster. If it doesn't have enough room, or you feel like you want to do some more intense, maybe grid search or AutoML, which will require more memory, you can shut it down and then start up a new cluster with a larger number of nodes or more memory per node.
Thank you. Is neural net implementation in H2O using any other framework like TensorFlow or an H2O implementation?
H2O's neural nets do not use any other implementation. So if you go to our models and deep learning, it is not using anything like TensorFlow. It's actually using our own algorithm written in distributed Java. It's a fully connected feed-forward neural network, which works very well for, let's say, structured data. Yep, and we do have a series of different parameters how you can play with this. You can specify the number of hidden layers, the activation function, the number of epochs used to train. You can get variable importance. And just like all of the other algorithms, you will get that Java export of this feed-forward neural network, as well as different graphics and metrics of how well the model performed.
Thank you, Megan. The next question is about driverless AI. Does driverless AI work only on GPUs, or can it work on CPUs as well? Would it work with CNN models for imaging?
Great question. So let me switch over to our driverless AI. So one of the things you'll notice in our driverless AI is that we do have this enable GPU button. It does not require GPU, so you can use CPUs. However, it is optimized for GPU, so you will probably see a speed up if the data is larger. So it does not require CPUs. The second question was related to if we have CNNs in driverless AI and if it can handle images. Currently, driverless AI only handles structured data. And what I mean by structured data would be a data set with rows and columns. It does not handle, let's say, images or audio. That being said, we do handle text data. However, it has to be a structured frame. So let's say you have a column with customer feedback and it could be free-form text. That's fine. Driverless AI can interpret the text and it will do text transformations on it like TF-IDF, but it can't just take unstructured data and build a model on that. Right now it needs, again, columns and rows.
Thanks, Megan. The next question says, on auto model, how is search done for hyperparameter space for each model? Is there some intelligent search that H2O does for this? AutoML
uses random discrete grid search. So it will actually randomly select different parameters and try those parameters and see how well the model performs. We have tested AutoML on many different open source machine learning data sets to figure out the best parameters that should be searched. But the search mechanism inside AutoML is a random discrete grid search. I would like to also add that AutoML automatically finishes building or running if it finds that it's converging early. So if it finds that the best models are not improving by a certain threshold, it will automatically stop that random grid search.
Thank you, Megan. Our last question asks, is H2O Flow available for students to download and learn?
Yes, Flow is able to, you're able to download Flow. So let me go to my H2O AI page. If you click on download, you can download H2O Flow. This is going to be in the H2O tab. Click on latest stable release. And just click download H2O. As I mentioned, this is just a jar file. It can run on your local computer, and here are the instructions for how to start it. If you are an R or Python user, you can click on the R or Python tab. For R, it's just the install packages function, and that will install H2O on top of R. For Python, it's a pip install function, so very similar to how you normally install packages. If you want to install us on Hadoop, you can just select the particular version of Hadoop that you're interested in installing it on and download this zip file on your Hadoop edge node. So there are many different ways you can install that. If I go back, we do have the sparkling water as well. Sparkling water is available for Spark 2.0, 2.1, and 2.2. So you can select your particular Spark version and then download Sparkling Water. Sparkling Water, as I mentioned, can run on Hadoop or a standalone cluster. We also offer R Sparkling and PySparkling. R Sparkling is our integration with Sparkly R, and PySparkling is our integration with PySpark. The last download tab I want to point out is Driverless AI. So Driverless AI is available with a free trial, a 3-week free trial. You can download that right here and select your particular version of CUDA. Before I move on, I did want to point out our documentations page for more information. Here's our H2O documentation. It provides information on H2O and a link to how to download it. This will give you information about all of the algorithms we offer, how to install H2O, and how to use it. So for example, we can click on an algorithm, we can click on GBM, and get information about GBM and how it works and the different parameters mean. Okay, and going back, we also provide documentation for Sparkling Water and also Driverless AI. So we can click on the Driverless AI user guide, and it will give you information on how to install Driverless AI in more detail in different environments, how to run an experiment, what do the particular experiment settings mean, how does accuracy affect the prediction or the experiment, how to score on another data set, how to view explanations, also more information on that scoring pipeline that we had discussed. So I would definitely recommend checking out our documentation page for more information.
Thanks, Megan. Before we wrap up here, I'd like to say thank you to everyone who joined us today. A special thank you to Megan for such a great presentation. A small note, the slides will be made available. If you're in the Bay Area, I'd love to invite you to join us at GDC San Jose to hear from the makers behind Driverless AI and H2O platform on the 28th and 29th March. For detailed schedule, please visit h2o.ai/community. Thank you, everyone.